Hello, and welcome back to the Cosmic Companion. In this week's episode of Astronomy News with the Cosmic Companion, we are pleased to be joined by Tyler Gorda of the Department of Physics at the University of Virginia, talking about his work discovering the newest state of matter, quark matter, which could make up much of the material in neutron stars. But first, we look at a new NASA study showing that oceans may be common on planets orbiting other stars. We examine a new study measuring the expansion rate of the universe, and a mysterious radio signal from space continues for more than 18 months. We'll also examine how dark matter, the unseen something, which makes up more than 80% of all the matter in the universe, might be detected here on Earth. Oceans may be common on other worlds, a new NASA study suggests. An examination of more than 50 known exoplanets, roughly the size of Earth or a little larger, suggests that up to 1/4 of all these planets are likely to contain large deposits of water. The James Webb Space Telescope, due for launch in 2021, could find large numbers of these water worlds and examine their atmospheres for the telltale signs of life. Since the Big Bang, the universe has expanded for more than 13 billion years. The rate of this expansion is one of the most important values for researchers seeking to understand the universe. One mystery is that the value predicted by theoretical physics for this Hubble constant is significantly lower than the rates actually seen by astronomers. A study utilizing an international network of radio telescopes lends additional evidence for this higher rate. This could suggest that some aspects of our standard model of the universe may need to be revised. In February of 2019, radio astronomers at the Chime Observatory in Canada reported finding a source of radio waves from space ebbing and flowing every 16 days. This signal, active for 4 days at a time, becomes quiet for 12 days before repeating the cycle. Now, 500 days after this discovery, the signal continues. Astronomers believe the radio waves likely come from a small, dense source, potentially one or more neutron stars, or a neutron star orbiting a black hole. Roughly 80% of all the matter in the universe cannot be seen. We know of this dark matter from its effects on stars and galaxies. However, a new Caltech study suggests this mysterious something can alter the magnetic spin of electrons, producing theoretical particles called magnons. This might allow researchers to see the effects of dark matter by using small detectors located deep underground. We are pleased to be joined today by physicist Tyler Gorda from the University of Virginia, who may have found evidence for an unknown form of matter. This week on Astronomy News with the Cosmic Companion, we are happy to welcome Dr. Tyler Gorda, a postdoctoral researcher at the University of Virginia. He recently produced a new study showing the existence of a potentially new form of matter called quark matter. Welcome to the show, Tyler.
Hi, thanks for having me.
Thanks. So just tell us a little bit, what is quark matter?
So quarks are inside, they're fundamental particles that sit inside of neutrons and protons, which are the things inside of the nucleus of a normal atom. Inside of a nucleus, you have quarks inside of neutrons and protons just sort of sitting there, and they're stuck, as it were, inside of neutrons and protons. They can't get out. And so really it's neutrons and protons moving around inside of a nucleus, and the quarks are not sort of free to move around, as it were. In quark matter, however, under enough pressure or temperature or density, it's possible, if you keep compressing the nucleus of an atom, to sort of melt the neutrons and protons and let the quarks out, as it were. Similar to like you can have a crystal, or if you have ice, the atoms in the crystal can't move around, but if you compress them hard enough, then you can turn it into like a different phase, where then the atoms inside can move all the way around. So your quark matter is just a term for when you free the things inside of these neutrons and protons to move around more freely than they can normally in an atom.
So what do we know about the properties of this quark matter? Well, I mean, if you could theoretically produce some of it, what would it be like?
So we actually know some things about it, even though it's so exotic. The calculations that we can do become simpler than they are normally, sort of as you keep applying more and more pressure and you have a higher density, the calculations get easier, and so we can say something about it. It's sort of easier to compress than normal nuclear matter. So normal neutrons and protons are sort of more rigid. If you try to increase the density, the pressure, you need a lot of pressure to do it. It's a little bit easier to compress this quark matter. We also know something about the speed of sound in this quark matter. It's very close to, well, the speed of sound squared. So the speed of sound times the speed of sound is around 1/3 of the speed of light. That's something else we can calculate. And it also, because there are multiple quarks inside of each nucleus, we know that there are more sort of free particles moving around in this quark matter than there are in the nuclear matter that it came from. Because basically, more or less for every one every one neutron or proton moving around originally, now you have 3 quarks or something like that.
Right. So did we know anything about like what sort of properties you would see with the speed of sound being so close to the speed of light? Would anything weird happen with shock waves going through it, or what do we know about that?
Just on its own, probably nothing weird, but what we're hoping in our study, so what we did was we said that we found some evidence for these 3 properties that I delineated. So the softer, easier to compress, this particular speed of sound value, and also this more free things moving around. We found some evidence for those properties sitting inside of neutron stars. And the fact that above that in the neutron star, there's some other matter, and below that, there's this quark matter, that interface, that could have some observable properties where you could have shocks or something there, but maybe we'll get more to that in a second.
Right. And so let's get into a little more about that. How are, just for those who may not be familiar, can you just give us a brief rundown on what are neutron stars and how does this change our picture of them?
Yes, so neutron stars are sort of the dead remnants of very massive stars. A star goes through its life, and it can end its life in a couple of different ways depending on how massive it originally was. The most massive ones tend to explode in supernovae, and what's ever left of their core, which has a mass of a few times the mass of the sun, like 1 or 2 times the mass of the sun, gets left over, but it's very, very compressed. It's something like a radius or a diameter of something like 20 kilometers, which I think is like, I should have done this conversion before talking to you, but something around
about 12 miles or so, I think.
12 miles, okay. Good.
Something like that, yeah.
Yeah, so it's The
About the
mass of
size
the
of a city.
sun, right? The mass of the sun, but in the size of a city, which is of course ridiculous. Um, now, because it's so small, it's very, very dense. The outer layers of it are as dense as the nucleus of an atom already. And as you go in, it gets even denser. So we know something about the outer structure. There's sort of atoms or nuclei, like I said, and then below that you start getting these nuclei in a crystal, sort of like, so you have regular arrangement of nuclei. And then as you go down a little bit farther, you start getting, so first of all, you can have sort of exotic nuclei that sit there. So they could have more neutrons than are normally stable. So normally if you have a nucleus with too many neutrons, it sort of, the neutrons fission out and it decays. In a neutron star, because there's so much pressure holding it in and so many extra neutrons, these can be stable. But eventually, if you go a little bit, if you go, so this deepness that I'm talking about is sort of the outer 1 kilometer, so outer like half a mile or so. As you go deeper and deeper, you get more and more neutron-rich nuclei, and then eventually you have too many neutrons to be stable in those nuclei, and they start coming out. Then you have this sort of lattice with some free nuclei or free neutrons moving through it. And as you get deeper and deeper, it starts becoming non-uniform. So you have like these pockets of, where you have like these extended nucleonic like sheets, or this is called pasta phases. This isn't the particular type of the particular part of the neutron star that I study, but it's very interesting in its own right. And then as you get into around a half a mile or so into the star, you have just uniform nuclear matter. So that means whatever is in like a normal nucleus, but just everywhere. There aren't any gaps like there are in normal atoms where you just have a little nucleus and then electrons going around it. It's just the whole like chunk of the star is just lots and lots of neutrons and protons all crammed as tightly as possible.
Right, right. Like that. Yeah, sort
Yeah.
of a soup.
Yeah. And then the question, so this we know pretty well from other calculations and experiments of how neutrons and protons behave on Earth. But as you go deeper and deeper, the question has always been, what happens as you just keep this chunk of nuclear matter under higher and higher pressure? Does it sort of melt into quarks and gluons, or does it not? So that's where we sort of were before this study.
That's pretty cool. So how close, I mean, how rare are neutron stars, and how close is the nearest one that we know of?
That's an extremely good question. I don't actually know the answer to that. I know, so a lot of neutron stars have a strong magnetic field, and as they spin, they sort of sweep this magnetic field around, and there's certain angles. When it sort of points a particular part of its magnetic field towards Earth, we might see a pulse of radiation coming from it. These are called pulsars, and that's sort of how scientists originally found neutron stars in the sky. I mean, they're not particularly rare. I think there's at least like dozens or hundreds, I would say, that we've been able to find this way that are, I think, within our galaxy. But I don't know exactly how many there are, but they're not incredibly rare.
And what got you interested in this research?
So I've always been interested. So I'm technically a physicist, but I've always been interested in astronomy also. You might expect those fields to be more similar than they are, but in some ways they're actually quite different. So I've been interested in astronomy, so I've known about these stars as sort of astronomical things for some time. So I've always been interested in just the sky and things like that. And neutron stars are particularly interesting to me because they're just so extreme. There's a ton of matter inside a small sort of size, like I said, but that also means that you have very strong gravity. Very strong gravitational fields lead to all sorts of strange behavior, like curving of space-time and having light sort of deflecting and giving strange behavior around these objects that you wouldn't expect from a normal star that has a similar mass but is just larger. In this particular study, I like it and was interested in it because we've been trying to, we're starting to get some new data from neutron stars because of the gravitational wave detections that maybe you've heard of in the past few years of colliding neutron stars. And that's allowing us to see them in a completely different way and measure things about them in a completely different way. And with this study, we were able to combine sort of some observations from there along with some direct sort of visual observations. And we tried to constrain things without needing to assume too much about the matter inside of them. So there's a lot of groups that are interested in trying to study exactly what the matter inside the core is like by sort of guessing what it might be like and doing calculations and seeing whether they agree. The approach that we took was to try to remain as agnostic as possible about what the properties may be, and then try to see whether we could sort of chip away at the range of allowed behavior and see whether we could get the neutron star and the data itself to tell us what the properties were like, rather than sort of putting it in and then checking it. It allows us to then, instead of having to be very clever about coming up with models, it allows us to sort of let nature tell us something about what the matter is like, and then we could go try to understand that.
And so you're using simulations as one of your technologies to to understand the behavior of these stars and to quark matter, but are there also can you talk a little bit about the technology you're using now, as well as other possible observational technology that could be used to further the study?
Sure, yeah, so what we actually used our particular group, we didn't actually use very much technology in this study. We sort of just used a normal computer to generate lots and lots of possible behaviors of the matter inside of the stars, and then constrained it. In the future, there are some groups doing some very interesting studies of numerical simulations of the whole collisions that these stars can undergo with each other when they collide, and then give these signals that we can see in gravitational waves. And one thing I'm hoping to do is to talk to people who do those sorts of things more, and see whether we could both give them better input, since they need to assume something about the matter as they simulate it, and also have them give us some ideas of either more interesting things that we could provide them with based on the way that we study it, or also just basically just trying to interface more with the people who actually do these simulations of mergers themselves.
Right. That's fantastic. Well, thank you very much. It was great having you on the show, Tyler.
Thank you very much for inviting me.
Yeah. And that was Dr. Tyler Gorda of the University of Virginia. This is the final episode of the second season of Astronomy News with the Cosmic Companion. We will take 2 weeks off as we move into a new, larger, permanent studio. The show will return on July 14th for the start of Season 3, when we'll give you an inside look at the James Webb Space Telescope. Scott Lambros, NASA's Instrument Systems Manager for this revolutionary telescope, joins us on the next episode of our show coming July 14th. We hope to see you then. We are also pleased to say that the Cosmic Companion has just been accepted as a trusted source of space and astronomy news for Google News. We look forward to seeing you there. Please stay safe, stay healthy, and keep your wonder alive. If you enjoyed this episode of The Cosmic Companion, please download and share the episode on YouTube, Facebook video, or on any major podcast provider. For more details on space and astronomy news, please visit thecosmiccompanion.com or thecosmiccompanion.net.